And hello, everyone, and welcome back. This will be our first day of death and destruction. So, volcanoes, and then earthquakes. And it just occurred to me I forgot to get the volcano lab ready, so I'll do what I did last time. I'll stop this lecture and I'll get that up, and then I'll tack that on to the end because I know how to do that now. So, volcanoes. Okay, so we'll do volcanoes, we'll do earthquakes. We'll do geologic time, and that will be it for our geology. I've got the test scheduled. It's on the course calendar. It slips my mind right now when it is, but y'all can look at the course calendar and see. I'm not springing it on you. We've got some time because I need to write the dang thing. So anyway, and so we'll have a volcano lab. I've got an earthquake lab. It's an online lab that we'll do. The geologic time lab kind of requires that I be there with you. We usually do it as I'm lecturing. That's not going to work. And so, unless I can figure something out, there probably won't be a geologic time lab. So, unless I figure something out. So, we'll see. Okay, so volcanoes. Volcanoes. Let me see. See, there's always that first advancing the slide when it doesn't want to go. What the heck, computer? We got this? There we go. So yeah, so what a volcano is it's a region where you have molten rock coming up to the surface of the earth. And we've kind of already talked a bit about molten rock when we talked about igneous rocks, but let's make sure we get this now. The reason I'm saying molten rock and not lava is because there's actually two different kinds of molten rock, right? Lava and magma. Lava is above ground, magma is below ground. Um, Now, for the longest time, I felt like this was kind of stupid because, why are you giving something a different name just because it's below ground? That doesn't really seem to make any sense. But it does make sense because look, magma is not just buried lava. Okay, molten rock comes up from below, and once it breaches the ground surface, it degasses. Right? You get a lot of gas content in there, and that gas escapes. And so yeah, the gas escapes, and now it is compositionally different. And so it gets a different name, right? It behaves differently. It does all kinds of things differently. And so we give it a different name. Now, some volcanoes, not a big deal, right? The volcanoes in Hawaii, right? Mauna Loa, Mauna Kea, all those volcanoes, they're erupting a lot. I mean, they're not erupting right now. I just checked, but they are erupting a lot. And no one dies in those volcanoes. Heck, what, 2, 3 summers ago, they erupted all summer long, and zero people died. Okay, so they're not very dangerous. But on the other hand, Mount St. Helens killed a whole bunch of people. Vesuvius killed a whole bunch of people. Fuego erupted a couple summers ago, along with Mauna Loa in Hawaii. It killed a whole bunch of people, and so there's a wide difference here in the hazard that volcanoes represent to people. And so we want to kind of understand why some volcanoes are so very dangerous. And other ones just are not, right? And so the key to understanding this is a property called viscosity. And viscosity is resistance to flowing, right? Highly viscous liquids don't like to flow. Low viscosity liquids, on the other hand, flow no problem, right? It's the difference between honey and water, right? Honey is a liquid, but it's high viscosity, right? Water, on the other hand, obviously also a liquid, but very low viscosity, right? If I have a jar of honey and I turn it, upside down on top of my computer, I've got a while before anything bad happens. It might not even come out of the jar, right? On the other hand, if I take my cup of water, turn it upside down on top of my computer, I pretty much need a new computer right away, right? So they're both liquids, but the difference is viscosity, right? And you can see lavas or magmas, molten rock, comes in high and low viscosity versions, right? At the top here, you can see a low viscosity magma, or lava rather, just flowing out of this vent. Let me get my pointer finger going here. You can see this just flowing out of that vent, flowing down about the consistency of a milkshake, which in the scheme of things isn't terribly low viscosity, but in the scheme of lavas, it is pretty low viscosity, so flowing down there. And then you can see a high viscosity lava down here that basically looks like a big pile of burning rock. Okay, it is moving, but it's moving, inches per day, or let's be all metric and say centimeters per day. Okay, so yeah, low and high viscosity lavas or magmas. So the trick here, of course, is that highly viscous volcanoes erupt violently. It's almost like a little haiku poem, only it's not the right number of syllables, but you get the idea. And so, if you have a lava or a magma that is high viscosity, pressure builds and it builds and it builds. And then finally, when it gives big, right? This is the volcano you see here is Mount St. Helens back in 1980. And yeah, right, high viscosity, massive explosion, lots of people dying in this volcano. On the other hand, low viscosity magmas or lavas produce volcanoes that are not violent, right? We're back to Hawaii. You can see lava just kind of oozing out. It's just not a problem, right? And so whether or not a volcano is violent is going to depend on the viscosity of its lava or magma. So what controls viscosity? Well, there's a few things actually that do. For example, temperature, right? If you want to get that honey out of that jar, stick it in the microwave for about 30 seconds, and I guarantee you it will pour right out of that jar. So temperature matters. In lavas and magmas, water content matters, other volatiles matter. But really, honestly, the thing that we're going to concentrate on, because it is the main thing, is silica. SiO2. It is that same stuff that we tracked when we tracked igneous rock composition, right? We talked about igneous rocks and we said, okay, well, look, igneous rocks that don't have a whole lot of silica, we're going to call that mafic. Igneous rocks that have a bit more silica, we're going to call that intermediate. And if they have more beyond that, we're going to call that felsic, right? So that's what we were tracking. Well, that's what we want to track here too, is that silica, because here's the trick, right? There's that silicon oxygen tetrahedron, right, that we talked about when we talked about minerals, right? That one silicon atom surrounded by 4 oxygens. And then remember this, remember that we had a diagram that looked something like this when we talked about minerals, where we realize that if you have more silica, right, it makes these more complicated molecules. And these molecules, they don't want to move. As they get bigger and more complicated, they stop sliding past each other. And when molecules stop sliding past each other, that's viscosity, right? That's what makes liquids high or low viscosity, is how well do those molecules slide past each other. Water is a relatively small polar molecule. It'll slide no problem, right? These silicon oxygen tetrahedra, though, as they get, larger and more complicated structures, they will literally catch on each other and literally will not flow. And so the more silica you have, the more complicated these structures get, and the more viscous your lava or your magma becomes, and therefore the more explosive your volcano is, right? So more silica means more viscosity, means more explosive, right? And so yeah, so we can then relate the viscosity of a lava or magma to the explosiveness. Sorry, let me say that again. We can relate the igneous rock composition of a lava or magma, mafic, felsic, intermediate, right? We can relate those to the potential explosiveness of the volcano, right? Mafic magmas, not a whole lot of silica, right? Let me go back here. Mafic magmas are made, or mafic rocks, mafic magmas are made of these minerals up here. Olivine, pyroxene, amphibole, things like that, right? And so not a whole lot of silica, not very complicated structures, and so yeah. So excuse me, gonna cough. Promise I'm not dying. And so those magmas, not a lot of silica, not very complicated structures, they flow just fine, right? think Hawaii. I know those Hawaiian eruptions look very, very spectacular, but they're not. I mean, they are, but they're not. They're not deadly. They're not killing anyone. Okay. Felsic magmas, on the other hand, now here we are at the other end of the spectrum. Okay. Felsic magmas have a lot of silica, right? If I go back here, felsic magmas are down in here, right? Down in here, right? And so now we have a lot of quartz, we have a lot of feldspar, we have a lot of mica. These are big, complicated molecules. They don't want to float, right? Felsic magmas are so viscous, they don't usually make volcanoes, right? Felsic magmas usually cool underground. Right? Felsic magmas make Stone Mountain, right? Big old honking piece of granite, there it is, right? That was never a volcano, right? And if we think about this, if we think back to igneous rocks for a second, everyone's heard of granite, right? That's the intrusive felsic rock. That's the rock that would cool underground. Everyone's heard of granite, right? People have granite countertops, granite this, granite that. There's granite everywhere. Not in Florida, but there's granite up here. There's a bunch of it. There's just granite everywhere. Right? It's a very common rock. What is the extrusive rock? If that granite were to have breached the surface and cooled quickly, right, made a volcano, right? What's that rock? Well, that's rhyolite. No one's heard of rhyolite. Y'all never heard of rhyolite, right? You didn't hear of rhyolite until I said it, right? It's not rare, but it's uncommon. That's because those felsic magmas don't usually breach and make a volcano. And if they don't breach, it is not a volcano, y'all, right? And so yeah. Now, so if mafic magmas make not dangerous volcanoes, and felsic magmas just don't make volcanoes, then what's the problem? Well, the problem are intermediate magmas, right? These are the ones that have, little enough silica that they will flow, but they have enough silica that they will breach and they will be explosive. Okay, so these are the ones, these intermediate magmas or intermediate volcanoes, these are the ones that we really want to look out for, right? This is that volcanic setting wherein people die, right? And so, yeah, so how do we do that? How do you make an intermediate composition volcano? Well, what you're going to do is you're going to mix mafic seafloor. Remember when we talked about tectonics and I said this seafloor is made of basalt or something like it. That's mafic, okay? And then we're going to mix that mafic seafloor with that felsic continental crust, right? And so the seafloor goes down. It melts down here. That rock begins as mafic down there and works its way up through and then breaches, incorporates more and more silica as it does, so that by the time it reaches the surface, it's intermediate, right? So that's how we do that using the drawing that we've been using, that you're used to, right? We've used this for plate tectonics, we've used this for all kinds of things, right? And so magma comes up, y'all know that, and then that plate's moving that way. Earthquake, shallow to deep along the Wadati-Benioff zone, melting, and then what begins down here as mafic will melt this granitic or felsic crust as it works its way up through, and by the time you're at the surface, now you've got an intermediate composition volcano, right? So these are the ones that you want to look out for, right? What I did was I combined mafic seafloor with felsic continent, made an intermediate rock and an explosive volcano, right? And so, I don't want to spend a whole lot of time here on Google Earth because I just don't. But let's take a look real quick at that, because I know that I've got it up. And so, if we want to see where this is happening, let's just look in the United States, because we've kind of done a lot of this. So if I kick into volcanoes here and we look, right? So here, right, you've got all these volcanoes of the Cascade Range down through here. And so what's happening here is, you've got the little Juan de Fuca plate out here, which is mafic. It's getting shoved underneath North America here, which is felsic. I combine that mafic seafloor with that felsic continent, and I get intermediate volcanoes, right? Same thing. I cannot help myself. I'm sorry, guys. Let me just do this one. I know. Right down here, right? Same thing down here in South America, right? This is why we get these very explosive volcanoes down here in South America. Same thing, right? Mafic seafloor out here, only now it's the Nazca plate or the Cocos plate, actually Nazca plate. Nazca plate out here. South American plate here, continental portion of it, right? Mafic seafloor, Felsic continent, intermediate volcanoes down through there, right? And and we could go other places. Let's not, right? And so that's where you get that those intermediate volcanoes, right? They happen at ocean continent convergent plate boundaries. Alrighty, so let me get the PowerPoint back here. Let's motor through all this. We've seen all this, and there we go. So, what about Hawaii? Right? I will not go back to Google Earth, but what about Hawaii? Right? I mean, we understand the Cascade Range volcanoes. We understand, the Andes volcanoes, right? Those are all ocean. I mean, we get that. We get Iceland. That's a divergent boundary. I mean, we've been through plate boundaries, and so we understand volcanoes with plate boundaries. Hawaii is nowhere near a plate boundary. It is. I mean, it is in the middle of the Pacific tectonic plate. And so what's going on here? Well, this is a particular kind of volcanism called a hotspot. Hold on, let me drink some water here. There we go. Okay, so this is a particular kind of volcanism called a hotspot. And what a hotspot is it's a region where you have a plume or a tube, if you will, of magma coming up under a tectonic plate. It'll burn through and create a volcano on top of it. Now, the thing to keep in mind, though, is that the plate moves on top of that hotspot. And so what you will end up with is a string of volcanoes. And I'll show you here in a minute how that works. So here, when you think about Hawaii, you also want to keep in mind that it's not just the visible Hawaiian islands down here, right? Once again, let me get back to my snazzy red pointer. So it's not just the visible Hawaiian islands down here, right? It's, the entire Emperor Seamount chain that runs all the way up into the Aleutian Trench up here, which you can't see on this map, but it is there. And so these are all related to each other, and these are all caused by that hotspot. And so, if we look at the ages of the rocks in Hawaii, we notice a very distinctive pattern. We can see that the rocks down here on the Big Island are very young, right? Like, right. Look. These are 0 million years old, right? They erupted just a couple years ago, right? But if I work my way to the north and in particular west here, assuming north is up, which it is, you can see that the rocks get older, right? 1 million years old, 1.7, 1.9, 2.63, right? The rocks are getting older as I move this way. And so this is going to provide us with a valuable tool, but we first really kind of want to understand how this is happening, right? Here's a snazzier picture of the Emperor Seamount, rather the Emperor Seamount chain and the Hawaiian Islands, right? And you can see how the Emperor Seamount chain goes all the way up into the Aleutian Trench, okay? And then here you can see, here's the hot spot down here coming up, making an active volcano here. And then, these dormant volcanoes strung out here used to be sitting over that hot spot. Okay, let's take a look. So normally this would be where I would get off of my chair and turn around and start drawing on the board, but I obviously can't do that. So I did a little animation thing. So what we've got here is we're looking. I know it's a silly little animation. Bear with me. So we've got the Pacific plate here viewed from the side. And we've got a hot spot bringing magma up here and causing an active volcano here. Okay, now, the trick here, though, is that this volcano and this plate slide, right? They move, okay? And so, that tectonic plate is moving this way, in this case, to the left. Okay, now, so what happens next? Well, what happens is this moves off, and it moves over here. Now, I can't, just in making the animation, it was a lot easier for me to move the hot spot and not the plate, right? But it's just a relative thing, right? So don't, the plate moving to the left is the same as the hot spot moving to the right, right? And so I slide this plate over the hot spot, right? This volcano goes dormant, right? No longer got a magma source, right? This now we make an active volcano. Okay, let's slide it again, right? So I'm going to slide the plate to the left, which is the same as moving the hot spot to the right. So the hot spot's going to move over here. So let's slide it again, right? So this volcano goes dormant, right? These volcanoes start to get a little bit smaller because they're being weathered away. In the case of Hawaii, by the Pacific Ocean, active volcano here. See how this is working out? You end up with an active volcano on one end of the island chain, and then dormant ones strung out behind it. Let's do it one more time. Let's shove the plate to the left, which is moving the hot spot to the right. So I do that one more time. There we go. Right, and so you can see I've got an active volcano here on one end and a string of dormant ones strung out behind it. Okay, so now let's think about this for a second. This is younger, right? This is, this volcano is erupting now. It is 0 million years old. This volcano out here erupted who knows how long ago. It is older, right? If I draw an arrow from the younger to the older rock, notice that it is going in the same direction as my arrow for the direction of motion for the tectonic plate, right? This is the trick here, and you're going to do a lab where you're going to need to do this. So just let me say it over and over again, or at least a couple more times, right? If you want to know what direction a tectonic plate is moving over a hot spot, draw an arrow from the younger rock to the older rock, and that will tell you, right? It works in map view too, right? If I put, the Hawaiian Islands here, now I tilted this, so north is not up on that little bit that I just put underneath there, so keep that in mind. But anyway, if I it works in a map view too, right? Looking down on the Hawaiian Islands now, if I draw an arrow from the younger rock to the older rock, that tells me what direction that tectonic plate is moving. Okay, now, once again, north is not up here, so this plate is not moving due east. Okay, so keep that in mind. Okay, so, but it's a very, very handy thing, right? This rock out here is about 5 million years old. This rock up in here is 0 million years old. And so if I draw an arrow from the younger rock to the older rock, that's the direction the tectonic plate is moving in. So it's a very handy thing. The other thing we can do here is we can calculate speed, right? If I know how far it is from here to here, right, I know how far this island moved in whatever its age is. I believe it's about 5 million years old. So I know it took this island here 5 million years to go from here to here. I know it moved in a curve. Ignore the curve. Okay, so it moved from here to here. Let's just, we're just going to, guesstimate at this. So if I know it took 5 million years to go from here to here, a little bit of division will tell me how fast that plate is moving. Okay, so, and that's going to be some of what we do in the lab for today. And so I will talk more about that here in a few minutes when I talk about the lab. Okay, so Hawaii is not the only hotspot. Hawaii is a great one. Hawaii is a very long-lived hotspot. Geologists, we love Hawaii. It tells us a lot of interesting information, but it's not the only one, right? Yellowstone is a hotspot out in the western, United States. This is a spring called Grand Prismatic Spring, and you can see why it gets its name. It is beautiful. This hasn't been photoshopped or anything. The colors are real. The red is iron, the yellow is sulfur, the green is copper, the blue is bacteria that eat the copper and the sulfur and the iron. Here's the boardwalk running past it just for scale, so there's some people. So this is one of the largest springs in the world, actually, and it really is spectacular. But Yellowstone is like that. Here's another spring, not nearly as spectacular, but you get the idea. And then there's also geysers out there, right? This is Old Faithful. This is a geyser that has a pretty regular eruption cycle. They've got a little clock, and actually you can download the Yellowstone app for your phone, and it will tell you, hey, Old Faithful's getting ready to erupt. Come on, guys, check it out. And so you show up, and yeah, there we go. Now what you don't see is there's people all around there. That looks like you're out in the middle of nowhere. Yeah, you're not. There's hundreds of people kind of in this semicircle around that geyser. It's just they do it like that so that everyone can take a picture where it looks like they hiked 6 hours to get to the geyser or something like that. So anyway, it is very cool though, very cool. And Yellowstone in general, guys, if you have a chance to go, you really should. So what's going on out there? Well, here's a map. And if we look carefully, we see a familiar pattern, right? Let me go back real quick. I gotta get past all this animation stuff. Right, so let's look at Hawaii real quick, and we see, 0 and then older and older and older as we work our way that way. Let me go ahead and see if I can do it this way so we're not having to go past all the animation stuff. So once again, 0 and older as we go this way. Let's look at that Yellowstone map again. And so if we look at that, we see bodies of rock that get older and older and older. Now, once again, let me get my snazzy pointer going again here. Right, we see bodies of rock: 630,000, 6 million, 10 million, 10 million, 12 million, 15, 16 million years old. Right, we see that same pattern. Okay, and if we draw an arrow from the younger rock to the older rock, I should go ahead and animate one onto here. But if we draw an arrow from the younger rock to the older rock, that tells us what direction the North American plate is moving, right? Here's a little arrow they drew up here showing it. Sure enough, it's moving to the southwest, and yeah, it is, okay? Now, the difference here being, though, is that with Hawaii, you have what are essentially mountains. They're mountains at sea, so they end up being islands, but they're essentially mountains. Here you don't have that, right? In fact, you kind of have the opposite. If you look at this, you got a valley running up through here, not a mountain range. And this gets us to kind of an essential truth about Yellowstone, I guess, is that it is a profoundly violent volcano, right? This is not, the kind of volcano that, builds mountains. This is the kind of volcano that blows mountains up. Okay, so yeah. And so you can see this valley running up through here where, eruptions, blew up the mountain range basically and created a valley running up through there. So yeah, Yellowstone, it's one of those favorite things on the internet. Every few weeks someone will show me an article. Oh my gosh, Yellowstone is overdue for an eruption. We're all gonna die. Run away. No, we're not. Okay, look, guys. It's not overdue for an eruption in any human sense. Okay, overdue for a geologic event means you could have a few million years still. Okay, so let's not get terribly upset here about Yellowstone. Now here's the thing: when it does erupt, it's going to be ugly. I mean, it's not pretty. It's not pretty at all. You cover fully half of the United States in volcanic ash, and bad things happen. But this is, once again, this is not something that is on the horizon, at least not for people. Let me show you something real quick. I have these up. So it is the job of the United States Geological Survey to monitor volcanoes. This is what they do. And so this is the Yellowstone Volcano Observatory, right? This is the people who are in charge of monitoring that. If they're not panicking, you don't need to be panicking, okay? I mean, you see all these, oh my God, we're all going to die next week. And then you go here and they're like, it's okay. It's just, hiccuping, whatever. So yeah. So here by the way, so here's the Yellowstone Volcano Observatory. Here's the Cascades Volcano Observatory. They keep track of the volcanoes in the Cascade Range. And then here's the Hawaii Volcano Observatory, keeping track of the Hawaiian volcanoes. And so we've got this under control, guys. Okay. So if you come across something online, or your crazy uncle shares you this article about how Yellowstone is going to erupt and kill us all, just come to the Yellowstone Volcano Observatory, take a look at it, see what's actually going on. Okay, and odds are it's going to look just like this. And yeah, so um, don't freak out about Yellowstone. It's an internet thing, right? Okay, so Yellowstone's beautiful though. I mean, it really is just beautiful. There's all kinds of animals out there. There's herds of bison, buffalo. I don't know what the difference is between a bison and a buffalo, but whatever. There's beavers. There's all. I mean, there's just all kinds of wildlife out there. It really is just fantastic. But you can also see back here, all this steam coming up. There is a very hot body of magma down there. That's heating that water to make those springs, those hot springs, heating that water, to make those geysers. And so, when you when you walk around there, you don't want to jump up and down. It's kind of a very, very weird feeling, but nevertheless. So yeah, don't freak out about Yellowstone. Go visit Yellowstone. It is absolutely beautiful. Give yourself a couple days to see everything. Do some hiking. It's absolutely beautiful. And so yeah. So when we think about volcanoes, when people think about volcanoes, they probably think of a particular kind of volcano, this big cone-shaped mountain, but they're not all big cone-shaped mountains. There's three kinds. Actually, we could say three and a half, actually, but three for now, kind. The first, and by far the largest, are shield volcanoes. More water. Sorry, guys. Shield volcanoes. So these are big. These are huge. The good news is they're not very violent, right? Most of the material that they extrude is lava. And as we're going to learn here in a few minutes, lava is the least of your worries in a volcano. I know that it's what everyone thinks about. If I ask, if you go on the street and you just randomly ask people, how do volcanoes kill people? They're going to say lava. Guys, is not the lava. It is not the lava. So, but nevertheless, these are very big volcanoes. They're not violent, they're not dangerous, but they are big, right? When you think about this, when you think about shield volcanoes, rather, think about Hawaii. Right, and this is why it's called a shield volcano. It's like, imagine a shield like Captain America has, or something like that, right? Where it's very, very wide and not very tall, right? Or they are tall in absolute terms, but relative to their width, right? They're a lot wider than they are tall. There's how you say it, right? And so they kind of have a profile kind of like a shield. They are absolutely huge, though, right? I mean, there's a cross section through Mauna Loa, the big island in Hawaii, right? Versus, Mount Rainier, right? Which is, a pretty big cone-shaped volcano. Mount Rainier is what people think about when they think about volcanoes, right? This big cone-shaped mountain. But you can see how it is absolutely dwarfed by Mauna Loa. And then we'll talk about Sunset Crater, which is a cinder cone. But yeah, so these are really, really big. We've already talked about this volcano, right? This is Olympus Mons on Mars. It is the largest volcano in the solar system, right? Remember, 80,000 feet tall, the size of Ohio. We talked about this when we talked about oceanography. And, it's kind of interesting. There's Ohio, right? And so that's how big Olympus Mons is. So, yeah. So, interestingly, though, if you were to ask me, well, how do you make a volcano that big, right? I mean, we're looking at Olympus Mons. This thing is huge, 80,000 feet tall, right? Everest is 29,000 feet tall. It dwarfs the largest mountain on the planet in terms of height. It's as large as all of the Hawaiian Islands. And so, if someone was to ask me, let's say 7 or 8 years ago, well, how do you make a volcano that big? I would say, well, that's because there's no plate tectonics, right? You get a hot spot, and that hot spot is just going to dump, right, all of this rock in one place, right? Imagine if you had all the rock that makes up all the Hawaiian Islands, all of the Emperor Seamount chain in one place, right? If plate tectonics had not shoved that thing off of that hot spot, you'd have all that rock dumped in one place, and it'd look a lot like Olympus Mons. So my nice pat answer that we were all, and it wasn't just me, every geologist, right, would say this, right? Now, it's that there's no plate tectonics, right? Yeah. Okay. So when we talk about not Olympus Mons, but when we talk about Mauna Loa on Earth, we have to say the largest above water volcano because of this thing here, the Tamu Massif. This is a volcano that is completely underwater. I know it has a weird name. Massif is just another word for underwater volcano, guys. Okay, and TAMU is Texas A&M University, where I went to graduate school. It's just sheer dumb coincidence. But anyway, the people who discovered it were from Texas A&M, and so they named it after their school. So the name makes sense if you know, but it's weird. But anyway, it's completely underwater, so I don't really have, any fancy photographs to show you, but I do have a side scan sonar image, and here it is. Here, sorry guys, hold on. And once again, no, I'm not dying. I'm just talking. Look, it's not like we didn't know this bump was down there. You're not going to hide a bump that big on the seafloor. But what we didn't realize was that it's all the same volcano. Okay, so with respect to scale, here's a little graph, and you can see that. First of all, Olympus Mons dwarfs everything, especially in terms of height. It's massive. Okay, there's Mauna Loa. Much smaller than Olympus Mons, not nearly as tall and not nearly as wide. Here's the Tamu Massif, though. Take a look at that. That thing is a little bit larger than Olympus Mons in terms of area. Not nearly as tall, but pretty dang big. And so, our sort of pat answer, you could never make a volcano that big on the Earth because of plate tectonics and things. Suddenly, that goes right out the window. So we don't know what's going on here. So even as we speak, the Joy Days Resolution, a drilling ship out of Texas A&M, I used to work summers on this ship. The Joy Days Resolution out of Texas A&M is out there drilling that volcano. No, they're not going to set it off. It's not like that. But anyway, I think they're out there now. I don't know. They might be somewhere else. But they've been out there drilling that volcano to learn more about it. And we'll talk more about the resolution and about ocean drilling when we talk about the ocean floor during the oceanography unit. But we are in the process of investigating that. Well, I don't do this kind of work because that's igneous. But anyway, though they are in the process of investigating this and working it out. But it's a fascinating thing. It really is, to have a volcano that big on the Earth where you really wouldn't expect to have something that big. If shield volcanoes are the largest, then cinder cones are the smallest. And seriously, guys, sometimes these things are 3 feet tall. I mean, they're not very big. They're not very big at all. They're often associated with other volcanoes. So you'll get fields of cinder cones, right? Most of what cinder cones put out is tephra. Tephra is anything solid thrown out of a volcano. So a lot of ash and a lot of rock. Not usually a lot of lava. Mostly ash and rock. But these are very, very common. And of course, the one that we all look at, or not of course, you've never seen this before, but Sunset Crater in Arizona. This is a large cinder cone, right? But, it's not that big, right? I mean, look, right? There's a tree, right? You could walk up it in, I don't know how long, not long, right? And so, yeah. Here it is compared to, Mauna Loa and Mount Rainier. You can see it's a little speck of a volcano there. But let's take a look at it on Google Earth, because I think it's worth looking at on Google Earth. And so let's go back to Google Earth. And the fun thing is, this is my Google Earth, so I got my place marks here. And so let's take a look at Sunset Crater. And we don't really need volcanoes. We don't need to kick that in. But here we are in Arizona, and there is Sunset Crater. Not very big. If I measure this thing, let's see. We'll take a line across it. That's fine. So if I go from here, to there, let's do it in miles because we don't know how big a mile is. There we go. It's almost a mile across, right? It's not that big, not really. But if we take so there it is. Now, if we take a look though, If I zoom out, suddenly I realize that's not the only volcano around here, right? The thing about cinder cones is they don't stick around long. Look, basically this is a pile of rock. Okay, and so it's gonna wash away. It's gonna be eroded away pretty quickly, right? So if we look around though, we suddenly realize, wait, this isn't the right. There's a good one right here. Right here, here's another one. Right there's a cinder cone. There's a cinder cone. And then when we start looking really carefully, we realize there's one that's eroded away. There's one that's eroded. Look, look, look. All of these are cinder cones. There's a bunch. This area is called the Valley of Fire, okay? Because there's all of these ancient volcanoes kind of, eroded away. And then if I zoom out a little bit and I come up here, I see another field of cinder cones, cinder cones, cinder cones. More. I mean, you've probably seen now 100 cinder cones. This is a fun one. Look at that. Um, this one, that it's not resolving very well. That picture's better than that. But anyway, there it goes. So this is a cinder cone called SP crater, and usually cinder cones don't extrude lava, but boy, that one did twice. Right? You can see the lighter gray, more weathered away lava flow here, and then the darker lava flow up here. So at least 2 generations of lava. I have a former student who's worked on this. I need to ask her if it's only 2 or if it's more. But yeah, I have a student who took my geology class a few years ago, went on to major in geology at USF, and she studies cinder cones. She's traveled all over North America studying cinder cones. Another cinder cone that's kind of famous, I'm going to show it to you now, is down in Mexico. This is a cinder cone called Paracutine. We'll give the screen a minute to resolve in here. And you can see this is another cinder cone. There's the volcano there with a lava flow, a pretty dang extensive one. And it actually covered over a village. We'll talk more about Paracutine very briefly, but it is a fascinating volcano. Grew up in a farmer's field one morning and then grew like 1,100 feet in a year. It was ridiculous, and then inundated a village with lava. So like I said, we'll talk more about that. So anyway, okay. So back to the PowerPoint. So cinder cones, not very common. I'm sorry, very common, not very big, and they occur in these fields frequently. So. But, right, the volcanoes you want to look out for, the ones that are always in the background whenever anyone draws a dinosaur. For some reason, there's always an erupting volcano in the background of dinosaur pictures. But these are called composite cones, right? And this is what, this is what most people think of when they think of a volcano, right? A big cone-shaped mountain. It's a combination of lava and tephra. So you've got some solid material, you've got some lava, They have different eruptive styles. They have what are called effusive eruptions, where they mostly just put out, gas and maybe a little bit of lava or something like that. And then, they have lava eruptions, Plinian eruptions, where they put out a lot of tephra. There's all kinds of different kinds of eruptions, but these can be very explosive. Most of them are around the Pacific Ocean. That so-called Pacific Ring of Fire that you always hear about is a lot of times these composite cone volcanoes. They are, as volcanoes go, medium in size, right? They're not as big as a shield volcano, but they're not as small as a cinder cone. These are the ones you want to look out for, right? These are the ones that when they erupt, they kill people, right? They're intermediate in composition, so they're viscous enough to be dangerous, but not so viscous that they don't even breach. So these really are the ones you want to look out for. So Mount St. Helens, of course, before the eruption, and then Mount St. Helens after the eruption. Same view, right? Before, after. Okay, so intermediate composition, composite cone volcano, very violent, and we'll talk a little bit more about this Mount St. Helens eruption. So, and then I said 3.5, and the half are fissure eruptions. right? These are just these long cracks with lava coming out of them. This was a big problem a couple summers ago in Hawaii. Those eruptions that you heard about were fissure eruptions. It wasn't like there was a vent. There wasn't. There were these cracks with lava coming out of them, and these can extrude an awful lot of lava. They can extrude an awful lot of gas, and in very extreme cases, they can be very, very dangerous. It's 3.5, but it's kind of an important half. So, okay, what are the problems, right? What are we worried about with volcanoes? Well, probably not what you think. So 6.5 ways to die in a volcano. So it used to be 6, but I added a half of one because it's kind of interesting. So anyway, so first of all, yeah, gases. Okay, now for the test, don't go memorizing gases. In fact, don't go memorizing really anything, right? Because it's an open book test, and so or open book, open note, open whatever you want. Just not the person sitting next to you. So anyway, gases, right? Remember that the difference between lava and magma is that degassing. So when that magma loses its gas and turns into lava, some of that gas is toxic. Now, some of it isn't. Right, water vapor is not toxic, right? But we're from Florida, so we know all about water vapor and humidity and things like that. Carbon dioxide, not necessarily toxic, but not good. That's the gas that's driving global warming. And by the way, no, it's not the volcanoes. The volcanic contribution to global carbon dioxide is tiny relative to humans' contribution. So don't blame the volcanoes. It's not the volcanoes. Sulfur dioxide is toxic. Hydrogen explodes. Carbon monoxide, that's what kills you in car exhaust fumes. Hydrogen sulfide gas is toxic, and I don't think you need me to tell you why breathing hydrochloric acid or hydrofluoric acid would be bad for you. Those are both very, very bad for you. And so, you want to be really, really careful around these gases, and a lot of them are heavier than air. So, you go walking down into a depression that you think is full of a nice 80% nitrogen, 20% oxygen mix, which is our air, and it's not. It's full of something else that's not good, and so you have to be very, very careful messing around volcanoes and with these toxic gases. The thing that everyone always thinks about when they think about what kills people in a volcano is lava. Not so much with the lava. It's hot, 2,000 degrees Fahrenheit, so it'll set things on fire, it'll melt things. But honestly, it doesn't usually move that fast. Usually, it's actually very predictable. It's like, okay, here comes the lava, right? Lava is not one of those things that comes tearing down the side of the volcano, looking to kill people. That's something else. We'll talk about that here in a minute, but it's not the lava. Once again, Hawaii, Mauna Loa mostly, erupted for like 3 months 2 summers ago and killed 0 people. Now, I'm not saying it's not dangerous. It is. You don't want to be around, right? Here it is. Here's this eruption, like I said, a couple summers ago. It's very destructive to property. It's definitely destructive to property. Your house is gone, but you're not in it because you saw it coming and you got out. And you even had time to pack up a little bit if you needed to. So, it is destructive, but it is not deadly. But nevertheless, I mean, you can see, up here, I'll get my little pointer thing going again. You can see up here, there we go, and you can see, this lava coming, and the very next day, it looks like that, right? Here, that bay right there is right there under all that lava. And so, yeah, so you can see this little bit here sticking up. The lava kind of went around that. I'll show you that on a map here in a minute. But despite, people being frankly rather stupid, no one was killed. Now, Few people came close, being on a tour boat, too near that lava. As that flows into the ocean, it cools dramatically and sometimes kind of explodes a little bit. And so you can see there some sticky hot lava went right through the roof of that boat and fell on a guy's leg, and he lost his leg. And so it was a pretty serious injury. But once again, they were way too close to that lava. You just don't do that. And so yeah, so water again. So anyway, 3 months of a volcanic eruption. 23 people injured, no one dead, and frankly injured because they were too close to the lava. Not so bad. Not so bad. Tephra, on the other hand, is a problem. Tephra is anything salt thrown out of a volcano. So it ranges in size from, ash, which is very, very small. Here's an individual piece of volcanic ash down here on the lower right? That scale bar is 30 microns. A micron is a millionth of a meter. And so imagine a meter stick, one of those sticks I had laying around the room. Divide that into 1,000,030 of those, right? It's very small stuff, and it is very sharp stuff. This stuff, I mean, you would think, between the volcanic bombs, which are pieces of rock that are feet across falling down, and the ash, you might be inclined to be more worried about the bombs. Don't be more worried about the ash. The bomb, I mean, you get hit with. I mean, very, very few people get hit with, falling rock. I mean, you're nowhere near the volcano. The thing about ash is, you don't need to be anywhere near the volcano. Heck, the volcano doesn't even need to be erupting. This ash can be dangerous hundreds of miles from the volcano. Volcanic ash is one of the few igneous rocks that has fossils in it, and I have extracted plant fossils from ancient volcanic ashes. And what I did was I just took a cube of it back to my lab and extracted the fossils in my lab because they were very delicate and things like that. But anyway, as I was pulling out the fossils, though, there was ash just rolling up into the air. And so I'm like, I'm getting a respirator, so I'm having to breathe through a respirator because I don't want to breathe that ash. I mean, it gets in your lungs and it literally rips them up from the inside. It's heavy, it's dense. So it collapses roofs and buildings and things like that. And it's just generally a real pain in the neck. It really is. Which brings us to this volcano, whose name I cannot pronounce. I've talked about this volcano before in class, so we'll just call him Bob. Bob erupted, oh boy, what year? 2000, maybe 2007, I think, something like that, around there. I need to look that one up. But anyway, Bob is here in the southern end of Iceland, and Icelandic volcanoes, as we will learn here in a few minutes, have a long and proud history of messing with people, in Europe. And so, this volcano goes off, throws a whole bunch of ash up into the air. A whole bunch. And the ash, pretty horses with ash behind them. The horses were fine, I'm sure. But anyway, there's some geologists driving through the ash. Here's some geologists sampling the ash. There are actually valid reasons to do that, but you notice they're not taking their helmet off. You do not want to be breathing that stuff. There's a Landsat picture showing where the ash is going, and it's going to Europe. And Icelandic volcanoes do this. They erupt and everything gets blown to mainland Europe where, it shut down air travel. You cannot fly through volcanic ash. You just can't do it. What happens is that engine literally melts the rock and you end up trying to fly with an engine full of igneous rock. And that is, as they say, a bad way to fly. And so, yeah, so I don't know, you think, let's go back here for a second. There we go. You think, well, look, here's the ash. Don't fly through it, right? That seems pretty simple. Okay, the problem is there's actually ash all around here with the apparently clear sky that you cannot see. And so, there's ash that you can't see. Your Doppler radar can't see it. You can't see it, and you're flying through it, and you don't realize it until your engine stops. And so, yeah, so much for that. Don't fly, right? And so this grounded air travel all over Europe, especially Northern Europe, for, I don't know, a couple of weeks. It was really something. Now, if we combine the ash with the most common of the gases that volcanoes emit. What we get is a combination of ash and water, right? You pump that much water vapor into the air, and you're probably going to make it rain. Volcanoes have a way of making their own weather, and it's not good weather. It tends to be rainy, lightningy weather. And so, if I rain down onto the flanks of that volcano that are covered in ash, I make a mud flow called a lahar. These are very dangerous, very dangerous. This was a weird thing. This was something that we kind of knew about because we had them in the rock record, but we didn't really get a really good chance to see one until Mount St. Helens. And there was I think I was if it was if I'm right and it was 1980, I was a freshman in high school, and what I remember is days of TV showing these mud flows flowing down the side of Mount St. Helens, and they're carrying logs, they're taking out bridges. I like this picture a lot because it shows how far up the tree the mud went, and there's a person wearing a yellow jacket right there to give you an idea about scale. So yeah, these are very dangerous, and they're still dangerous hundreds of miles from the volcano. The other thing is they take out bridges, and so if you're over here and you need an ambulance, and the ambulance is over here, you got a problem. And this was a big deal with Mount St. Helens. All the bridges were out. All the bridges were out, and there were people who needed help. They needed evacuating, and it was just a serious problem. So these lahars are definitely a thing. But the thing that really gets people is something called the pyroclastic flow. Pyroclastic flow is sometimes I find a little difficult to explain. So let me see. Let me do something here real quick. Pyroclastic flow is basically everything bad about a volcano. And yeah, I had the foresight to put this picture in here. So imagine that you are standing or hanging from a rope here, right, over that vent. That's pretty much the worst place you can possibly be, right? Everything bad about a volcano is happening there. Okay. It's hot. There's lava getting thrown up in the air. There's all those toxic gases. There's ash. There's everything. It's all bad. Okay. But it's moving up. No one lives up, right? A volcano can spew all that nastiness up all it wants. Okay, no one lives up, right? What a pyroclastic flow is all of that stuff that is normally going up coming down the side of the volcano, right? Very quickly, very unpredictably, and it is literally it is so dangerous. I mean, this is what kills people, right? It reaches you, you die. It is really that simple. Okay, I have a video that I want to show you, but I don't have it up yet. So I'm going to try pausing this, and then I'll be back in a minute with having the video up. Let's try this. Okay, guys, I'm back. I'm going to show you this video. I don't think the sound is going to be very good because it's just going to be running from my speakers to the built-in mic on the computer. I will also post a link to this video, so if you want to watch it with better sound, you can. But this shows a really good view of a pyroclastic flow. Marita and Katya Kraft were geologists. They're very legitimate volcanologists, traveled all over the world studying volcanoes, and they were killed in a pyroclastic flow in Mount Unzen. You're not going to see them die. Don't worry, I'm not going to show you anything like that. But you are going to get a really good look at a pyroclastic flow. So sorry. There we go. And so let me go ahead and make this bigger, and let me see if I can make it louder, because louder is good. Nope, everything's at 100%. Okay, I will post a link to this video as well, so that if you want to go back and watch it, you can. Okay, let's take a look.
In the volcano world, these are superstars.
I fell in love with volcanoes when I was 7 years old. I saw my first volcano with my father, and this was really a discovery for me. So I decided to become geologist.
I fell in love without seeing active volcanoes. I have seen films and photos and was interested in geology, and so I decided to be volcanologist.
The crabs hail from France, but home is wherever the earth breathes fire.
For me, an active volcano, especially volcanoes that I know very well, those are like friends. There is a sort of dialogue between the volcano and me. I don't know exactly why. When I see an eruption, sometimes it's so nice that I just drop my instruments and look. That is to say, I cannot only study the eruption. I want also to film volcanoes to show it to other people.
For me, the danger is not important. I am afraid when I go in a car, but on volcanoes I forget everything.
The crabs never denied the dark side of volcanoes.
I am never afraid, because I have seen so much eruptions in 23 years that even if I die tomorrow, I don't care.
Something triggers a pyroclastic flow about 10 times bigger than all that came before. Within moments, it overwhelms the valley. By the time a TV camera in the village records this scene, Maurice, Katja, and 41 others are dead.
And so Paul back here, and I wish this video was like 20 seconds longer, because this pyroclastic flow that you see here stops right there and drifts off to the right. And so yeah, but that's what that is. And I'm gonna let me hold on. Let me pause this, and I'll be right back, guys. I need to put my microphone back up and all kinds of other things. So let me just do this. Okay, so I'm back, and I'm back on my Bluetooth microphone. But and like I said, I will post a link to that video if you want to watch it with better sound. It's really kind of an incredible video. But anyway, so yeah, so this is what kills people, guys. This is it. This is the thing, right? All of that hot ash and rock and gas and everything flowing down at incredibly high speeds. They can flow over water. They can flow to some degree uphill. They really are just not good at all. And you know, there's a picture of a bunch of trees knocked down in Mount St. Helens from the pyroclastic flow. There's a pyroclastic flow in the Philippines. Here's an old picture of them. You know, for a long time we didn't really know that much about pyroclastic flows, because anyone who was near one died. And so it's really only been recently that we've had good video of these things, you know, from a safe distance and whatnot. And so they really are quite dangerous. You know, another thing, just, you know, I don't know, plain old landslide, right? I mean, volcanoes are steep-sided mountains that frequently have earthquakes underneath them, and so landslides. You know, both small-scale ones, like the one you see in this picture, which is relatively small scale, but also large-scale ones. And yes, I was right, Mount St. Helens was in 1980. The Mount St. Helens eruption began with the largest landslide ever in recorded history. And so you can see here, you know, the side of the mountain kind of bulging. What happened was there was snow on this mountain. And when the magma came up underneath it, I'm going to get back to my fancy pointer. When the magma came up underneath it, it melted the snow. That turned this into mud and mobilized basically the slope. And so a little earthquake, a magnitude 5 earthquake, we'll talk about earthquake magnitude next time. A little earthquake set off this landslide that was the entire north slope of this mountain sliding down, that unloaded the magma chamber, and you can see pyroclastic flow. These photographs taken within just a few seconds of each other. And you can see a huge lateral blast and pyroclastic flow coming out the side of the mountain. People were expecting Mount St. Helens to erupt. They were not expecting that. There were geologists on the side of that mountain still putting out instruments to measure this eruption when the eruption happened. So we learned a lot from Mount St. Helens. And people gave their lives to learn a lot about Mount St. Helens. So it's pretty amazing eruption, really. So now we monitor snowmelt, right? Because turns out that's important. So yeah. 0.5, I said 6.5. Sorry, I just yelled at you, didn't I? I apologize. 6.5, lightning, right? Volcanoes make lightning. And if you go on the internet, you can find all kinds of pictures of volcanoes with lightning, right? Some of them are probably photoshopped. This one is not. They just make lightning. And so, lightning is obviously, dangerous. I mean, there's Bob. This is an unpronounceable volcano in South America. I don't know, but anyway. And here's Bob in Iceland. Apparently, I can't pronounce volcano names. Also with lightning. Paracutine in Mexico. That volcano that I showed you down in Mexico with the big lava flow. Didn't kill anyone with lava or pyroclastic flows, but killed 3 people with lightning. And so, yeah. There's a picture of the village that got covered with lava with Paracutine. You can see in the background they're still erupting. It was a phenomenal eruption. Let me just talk about a couple more volcanoes and then we'll be done. Tambora in 1816. Now this is not Tambora. This is actually Pinatubo in the Philippines. But Tambora in 1816 was similar to Pinatubo because it was mostly an ash event. And so Tambora, I think I showed you Tambora before, is down north of Australia, down here in Java, down here south of Borneo. So there's Australia. There are Papua New Guinea is over there outside of the frame, and so the rest of Asia is kind of up here, and there is Tambora right there. If we look, this is a little bit old, but you get the idea. If we look at, there's a number of ways to reconstruct temperature, but if we look here, right here, where all of the temperature indicators drop, that's Tambora throwing up enough ash to block the sun, causing what came to be called the year without a summer, right? I mean, nowadays food security, is okay. I just had to check the year because I forgot 1816. 1816, food security, not so much. I mean, not really. I mean, I know we're all feeling a little insecure right now because, you go to Publix and those shelves, they don't always have exactly what you want. But let's face it, they got food. I mean, that you might not get your first choice of bread, but they'll have your second or third, and then, this is a temporary thing. But no, not so much. There wasn't any food. There wasn't any food at all. People starved all over the world because of the ash that Tambora threw up into the air. It really was just phenomenal. Vesuvius, an eruption that I think everyone's heard of back in 67 AD. Now, this is not Vesuvius in 67 AD. There was another eruption of Vesuvius during World War II. So if you Google Mount Vesuvius eruption, you're going to get a lot of pictures with World War II aircraft in them, right? 67 AD was not World War II. That was the Roman Empire, right? The Roman Empire did not have B-24 Liberators flying around. So anyway, but the eruption in 67 AD, I believe it was 67. I might be off by a few years there. But anyway, it took out 2 towns, Pompeii, which everyone has heard of, and Herculaneum, which no one's ever heard of. But this is Pompeii, and there's Vesuvius there in the background. This is not 2 mountains. This is 1 mountain that's had the top blown off of it. So a pretty severe eruption. Pompeii is kind of famous for these casts of people who died in the eruption. I've seen them, and they're creepy. They're very creepy. But what happened here was, so the volcano erupts, it kills people, but their bodies, by the way, with a pyroclastic flow, okay, and then their bodies are immediately buried with ash. Sorry, I'm thinking ahead about the exercise I want to get going. I'm not paying attention to what I'm doing. Their bodies are immediately covered with ash. And so now you've got a body inside entombed in that ash. That body is going to decompose. And so as it does, it decomposes over the years. And then what you're left with then after the body and the clothing and everything decomposes, you're left with a person-shaped hole in that volcanic ash. And then archaeologists later on, years and years later on, are excavating. And they're, hey, wait. There's a person-shaped hole in this ash. Let's pump some plaster in that person-shaped hole and make a statue of that person. And that's basically what you see here is plaster pumped into these holes that were made by people's bodies at the time they died. And like I said, I've seen them and they're creepy. They really are, but it is an extraordinary thing. Pompeii and Herculaneum both represent really valuable archaeological resources because they preserve, Roman trading towns at the height of the Roman Empire, and so they are archaeologically very valuable sites. I just want to mention Laki, which erupted in Iceland between 1783 and 1784. So now you're going, okay, where's the volcano? Okay, Laki was a fissure eruption. This right up through here is the quote-unquote volcano. Laki erupted in 1783 and 1784, killed half the livestock and a quarter of the people in Iceland. And then blew enough ash and sulfur dioxide and other chemicals over to Europe, caused crop failures over in Europe, in particular France, and a bunch of hungry French people decided to overthrow their government. We sometimes call that the French Revolution. In fact, we do call that the French Revolution. And so, I am saying that the French Revolution was caused by an Icelandic volcano. It wasn't, you can't really do that. But it didn't help. It definitely didn't help. And so, let me just a couple more pictures of Mauna Loa a couple summers ago. A really spectacular and amazing eruption. I would not be standing there. I'm just saying. I would not be standing there. But they are. Okay. But just, amazing pictures of lava flows. Very destructive, not dangerous, but very destructive. And then here's the final map for this event, and the purple is new, or I don't know, was that pink? The pink is new lava as a result of this event. Here's the fissure running right up through there. Remember that bay I showed you before when we were talking about lava? There's that bay right there. This dotted line here is where the beach used to be, and you can see that we've added a whole bunch of land basically to Hawaii, which by the way belongs to the state. They have a whole law about that. New land belongs to the state. There's that hill I showed you in that picture showing the bay getting inundated with lava. And so this was 2018. There's a year. So anyway, water. So anyway, at the same time, Hawaii was erupting. Fuego in Guatemala was erupting. Fuego burped out a couple of pyroclastic flows. Burped out. That's a weird way to say that, isn't it? Fuego put out a couple pyroclastic flows that killed a couple hundred people. It was a very violent eruption. Frankly, I was a little bit unclear because I was like, why were those people there? Why weren't they warned? Why aren't they keeping better track of these volcanoes? Well, it turns out that Fuego is actually one of the most active volcanoes on the planet. And so people were kind of used to Fuego erupting and doing things. And so, this was, the fact that Fuego was erupting was kind of like routine. The pyroclastic flow was not. And so people got caught by surprise by the pyroclastic flow. And so, a very, very dangerous volcano. Mount St. Helens before, during, after. We've seen these pictures before. I want to move my little pointer thinger. There we go. And, there's a visitor center right in the path of the explosion of the pyroclastic flow now. But it really is beautiful. There's hiking trails and flowers. You should go. You should check it out. It's really very cool. Really very cool. And not done. Not even remotely done. This is a Landsat picture showing a what's called a lava dome in the middle. That thing is growing by about a dump truck load a day. And so Yeah, not done, right? And we understand the tectonic setting now, right? As long as the Juan de Fuca plate is getting pushed underneath North America, that thing has a lava source down there, and so, or a magma source, and so it's not done. It is by no means done. Okay, now that I learned that snazzy little pausing trick, I'm going to pause this for a second, and I'm going to bring up the lab, and I'll show you all what I want you to do. Hello, everyone. I'm back. And by the time you're watching this, this exercise will be unlocked. Hey, if you are in I forget what time my classes were. Oh my gosh, this is terrible. No, if you were in my Monday, Wednesday at 2 o'clock class, this is going to look very, very familiar because we did it when we talked about plate tectonics. Here's the problem. I never entered those grades, and they're stuck in my office, and I'm in North Carolina. So, guys, y'all do me a favor. Just do it again. Okay, you've already done it. You can bang it out pretty quickly. Do it again real quick. Stick it in Dropbox. I'd appreciate it. In my usual procrastinating way, I put off entering that lab, and like I said, it's in my office, and I'm in North Carolina. All my other lab sections, the other three of you, you've never seen this before. I was saving it for volcanoes, and so now here we are. So we're going to do a lab on the Hawaiian hotspot. So if you need to, or if you, let's say you maybe skip, no, you're listening to my lecture, so you didn't skip it. So if you need to, go back and look at that little animation thing I did with the Hawaiian hotspot. And so, yeah, so here's the deal, right? First of all, ignore the points, just ignore the points. Okay, so there's a little explanation, and here's a map, right, showing the Hawaiian Islands with, the big island here, and then islands getting gradually older as you work your way this way, right? And so what we're going to do is we're going to count. Let me see if it'll let me do this. Yes, okay. What we're going to do is we're going to calculate the speed and the direction of the Pacific plate over this Hawaiian hotspot, right? And so the first question I ask is, how old are the lava flows on Oahu? Okay, seriously, guys, read it off of the map, okay? All you have to do, right? Then I say, okay, look, use the map scale to determine how far Oahu is from the hotspot, right? And so here's the hotspot down here where the block is 0 years old. Here's the map scale, and so look, guys, we're not terribly interested in precision here, right? Just hold your fingers up to the screen. About that is 100 kilometers, so that's about 100 kilometers. That's about 200 kilometers. 300, etc. Right? Just use that distance as 100 kilometers. How far do you think it is from there to there if that's 100 kilometers, right? So put that here. Now, so we know time, we know distance. That's speed, right? If I divide this distance here by this time here, that will tell me how fast the Pacific plate is moving. Write that number right there. Okay, now, here's the trick. Okay, that is in kilometers per million years. That is a stupid, worthless unit. Right? If you say how fast are you going, and I say, oh, about 50 kilometers per million years, that doesn't, okay. Is that a lot? I don't even know. I mean, no, it's not, but you get the idea, right? And so what we really want to do is get that to centimeters per year. That's a nice, manageable unit, right? We all know how big a centimeter is. We all know how long a year is, right? Now, we could go through some fancy math. We're not going to do that. I'm just going to tell you, converting from kilometers per million years is just a matter of dividing by 10. So if you get 70 kilometers per million years here, this number is 7. Okay? If you get 69.5, the number down here is 6.95, right? Just jack that decimal one place to the left or divide by 10. It's the same thing. Okay? Simple enough. Now, what direction did Oahu move as it moved off the hot spot, right? That's the direction the Pacific plate is moving. Remember, if I draw an arrow from the younger rock to the older rock, right, that will tell me what direction the plate is moving, right? And so let me see here. So shapes, there we go. And give me an arrow, right? So if I draw an arrow from the younger rock, 0 million years old, to the older rock, right, that will tell me what direction the plate is moving, right? And so where's my format shape? There we go. And so let's make that a little bit bigger so we can see, right, from the younger rock to the older rock, right? And so there's a little north arrow right there showing you what direction north is. I hate these blue lines. Let's make it black. There we go. Okay. So, you know, as I said in that little animation bit, right? You want to know what direction a tectonic plate is moving over a hot spot. Draw an arrow from the younger rock to the older rock. That's the direction the plate is moving. Okay. Okay. So that works really well for like one volcano at a time. But look, we got data for everything. We got data for the entire Emperor Seamount chain. So, awesome. Okay, so what do we do with those data? Well, we graph them, right? Because, you know, that's what we do with data. And so we graph them. And you can see there that we've got a graph of those. Now, what I can do, remember the height and foot size exercise where we just kind of eyeballed a line through the data, right? If I do that here, I get a line right about there. Right, something like that, right? About half my points are above the line, about half my points are below the line. And so there's a pretty good regression line through those data. Okay, now, here's the trick. The slope of that line is the speed that the plate is moving, right? If let's just say that my line was down here. Then it's not, right? The data aren't there, but let's just say it was. So that means that in 20 million years, rather than moving this far, it only moved that far, right? So not nearly as far, not nearly as fast, right? Or on the other hand, let's say that my line was up here like this, right? Let me get it. Let me make that look prettier. There we go. Let's say that my line was up here, right? Now, in 20 million years, I moved further. Means I'm moving faster, okay? So the slope of this line, whatever it happens to be, is the speed that the plate is moving. So we need to calculate the slope of that line, okay? I'm going to guide you through that because I know it's been a while since we had to do. Ooh, that's weird. It's been a while since we had to do anything like that. Okay, so here I guide you through it. Now, what we need to do this are 2 points on this graph. Okay, I recommend using the first one, right? 0.20. This is the x value. That's the y value, and use the last one, right? 64.74860. This is the x, that's the y. Okay, so I guide you through this. I say, look, what is the y value of 0.1? Okay, let's use this for 0.1 because it's gonna we're gonna have to subtract. So that's 4860. Okay, so okay, I'm so I'm literally gonna do this. Okay, so 4860. Okay. What is the x value for 0.1? Well, it's 64.7, right? So let's do that. 64.7. Okay. So what about 0.2? What's the y value for 0.2? If I come up here, it's easy. Don't do that. It's easy. It's 0, right? So let's go with 0, right? So let's go with 0. You get that right? Hold on. Blah, blah, blah. Yeah, I am. Okay, sorry. 0, right? 0. Okay. And then what's the x value for 0.2? It's the x value for 0.2 is 0.2. Sorry, I've got 2 0.2s going on there, but 0.2. Okay, so there. 0.2, not 0.3. There we go. Okay. So now subtract these numbers, right? 4860 minus 0 is 4860, right? Subtract these numbers, 64.7 minus 0.2 is 64.5, right? Now divide them. Divide the kilometers by millions of years. That will tell you how fast that plate is moving in kilometers per million years, right? Subtract 4860. Here, let's just do this because I know y'all freak out about math a little bit. 0, okay? And then subtract 64.5 is what you get, right? So now divide, right? So divide the kilometers, so 4860 by the millions of years, 64.5. That will give you a number. By the millions of years there, that will give you that number in kilometers per million years, right? That's a stupid unit. Divide it by 10 to get it into centimeters per year, okay? Alrighty, so there, you just calculated the slope of this line right here, not the other two, that one, okay, to get the speed of the Pacific plate, the speed that the Pacific plate was moving on average over the last, 60 million years or so. Okay, so a couple more questions about direction. You can see here that there's a bend right here in that seamount chain. Right here's Hawaii, running up through here. Here's the bend, and then all the way up to here, right? And so, yeah, so I ask you, okay, look, note the bend. First of all, how long ago did the bend happen, right? Look, you have a volcano right there at the bend, Diakikuji, okay? If you find the age of Diakikuji up here in your data, that's how long ago the bend happened, guys, all right? So, yeah, so, there, right? So, there we go. Keeping in mind how plates move over hot spots, what direction was the Pacific plate moving between the formation of Meiji and Diakikuji, right? Meiji's up here, right? The rocks get older as you go this way. In general, the older rocks are up here, the younger rocks are down here, this one's somewhere in the middle. So, yeah, so once again, draw an arrow from the younger rock to the older rock. That tells you how fast the plate was moving, right? And then what direction since the formation of Diakikuji, once again, between here and here, draw an arrow from the younger rock to the older rock. This is 0. This is 40-something million years old. Draw an arrow from the younger rock to the older rock. That arrow points in the direction the plate's moving. There is not a north arrow on this map, but it is safe to assume north is up, which means west is to the left, east is to the right, and south is down, okay? Alrighty, so there's the exercise. By the time you all listen to this, that will be up, all right? Okay, so, alrighty, and okay, I will talk to you guys again. Earthquakes next. Okay, bye-bye.